Dr. Arun Sharma. He's working as the assistant professor in the Department of Food Engineering at the National Institute of Food Technology, Entrepreneurship, and Management in Haryana, India. His research interests focus on integration of machine learning with sensor technologies for food safety and quality monitoring. As a postgraduate electronics engineer by training, his interest in amalgamation of sensing technologies into agri-food sector was further stimulated when he had opportunities to participate and lead various technology fairs, conferences, along with participation in NIFTEM Village Adoption Program in different states of India. His extensive stay in villages as part of activities undertaken during VAP sharpened his understanding about challenges in agri-food sector from farm to fork, while industry visits depended on his automation and machinery expertise. This motivated him to concretize his doctoral research to develop artificial intelligence-driven, rapid, portable, and low-cost spectrophotometer for non-invasive quality prediction of fruits. He has mentored 6 research projects, authored 15 research papers in high-impact factor journals, 6 book chapters, and edited 1 book. Please welcome Dr. Sharma.
Thank you so much. Thank you for the invitation. Thank you for having me. Well, I was in UC Davis in the morning, so somehow while returning back, I missed my lunch. If you don't mind, can I have my lunch here, some little bits of snacks, if you don't mind? This apple is something raw, sour. Let me try this one. I have this one. Both are good. People say, and 1 apple a day keeps a doctor away. It has potassium in it, so that it will be good for heart. But I'm confused. Which one is highly nutritious? Can you help me out? Well, I do have a solution for finding out non-invasive quality estimation of fruits and vegetables. I have developed a portable spectrophotometer which is based on artificial intelligence. Well, thank you. Little bit of domain-specific introduction. I'll be quickly rolling over the slides to make a connection with the domain-specific food technology. Well, there are 2 types of fruits. First is climatic, other one is non-climatic. Climatic fruits are those such as apples, tomatoes, which ripen after harvest. Ripening after harvest means as soon as we keep the climatic fruits under storage, they do have some physicochemical changes in it. So as soon as physicochemical changes progress, the ripening advances. So ripening is genetically programmed, and once we harvest the climatic fruits, then after ripening during storage they reach to the horticultural maturity. Now there are 2 ways. One is destructive way. We can do it in the laboratory, find out various quality parameters, various physicochemical attributes. The other one is non-destructive test. I have chosen spectroscopy as my area of concern. Well, if you look at the spectroscopy per se, there is electromagnetic spectrum. So the sensor which I have used is Sparkfun multispectral chipset, which has range from 410 nanometer to 940 nanometer. It is within visible and short wave near infrared region, such that the waves, they penetrate into the fruit and come out. So as soon as, if you look at here, so the light waves, they go into the fruit. First of all, they reflect back. That is the specular reflection. It is on the surface. It is similar to kind what we take images. But the second one, B1, it is the diffused reflectance. That means it goes into the fruit and come out. While C and D, C is coming out, D is getting absorbed. So my concern is A and D, so that I have a specular reflection and the diffused reflection. So I capture these 2 and make machine learning models based on these received reflectance and find out the physicochemical attributes of the fruit. So apart from the literature which has been available, so till now the technology is not in the public domain, although many of the research is there. The research gap is the machine learning models which have been developed, by the researchers, they are not able to integrate back into those commercially available proprietary devices. So my concern is if I can develop open source platform. That is the concern. So I developed open source platform, hardware as well as software to investigate the physicochemical attributes of fruit using AI. So this is what I have done. I have used the SparkFun multispectral chipset with Arduino Uno board, and this is the spectrophotometer assembly. This is the cabinet I have been granted IPR in terms of design registration just on 19th of April by Indian government. So I captured the spectral data from 410 nanometer to 940 nanometer for the test samples, tomatoes in this case, because tomato in horticulture produced tomato is the most suitable produce to capture the ripening process of all the climatic fruits, including apples and other climatic fruits. So I have done laboratory experiments and the spectral reading, and then performed, then analyzed the relationship between spectral readings and the laboratory experiments, and then developed machine learning regression as well as classification models. So this study has been a huge and the most voluminous study in terms of data acquisition. So these are the physicochemical attributes which I have obtained in the non-destructive, in the destructive testing laboratory, where this is weight loss, color, firmness, total soluble solid, titratable acidity, pH, electrochemical salinity, total dissolved solids. Important is lycopene content. Lycopene content, it reduces the risk of cancer and osteoporosis disease. Then next is total phenolic content, flavonoid, antioxidant activity. So these all are the laboratory based data which I have collected along with the spectral data from the spectrophotometer assembly. So these are the tests. So this is the schematic of the spectrophotometer. This I would like to highlight that instead of just taking up the photo or maybe the RGB image, we can see as the spectral rays are bombarded on the target fruit, they go into the fruit and then come back. So in order to validate the spectrophotometer, I have validated it with Konica Minolta spectropolarimeter, and then the results are very promising. That means the spectrophotometer is in line, although it is much cheaper than colorimeter, because colorimeter of Konica Minolta uses a high-end lens to capture data, but still this spectrophotometer assembly is good to go. So in that case, physicochemical attributes and spectral data, then feature extraction, selection that which of the wavelengths are varying with respect to storage duration, normalization, splitting of data into train and test set, and then development of machine learning models. So in development of machine learning models, I have not enthusiastically switched over to apply AML. I have progressed slowly with the linear models. First of all, I do it for multiple linear regression model, partial component regression, principal component regression, partial least square regression. Then I move to nonlinear models, random forest, support vector regression, and artificial neural networks. So this is the relationship between different physicochemical attributes as well as the spectral data. So if you look at the spectral data, it is quite visible that the data is from day 0 to day 15 of the entire storage duration. And some of the spectral changes are there visible, but in order to identify which of the spectral data varies statistically significant, I have normalized the spectral readings and then obtained which of the wavelengths are varying with respect to storage duration. That means these are the candidate wavelengths which has to be involved in development of machine learning models. Further, I have removed the multicollinearity among those potential candidates. So this will allow the machine learning models not to be over enthusiastic. So I have removed the multicollinearity among the predictors of the spectral variables, spectral wavelengths. Then identified which of the spectral wavelengths give the best result in terms of machine learning, multiple linear regression for the color value A indicating the redness of tomatoes. Similarly, I have identified that these are the wavelengths which are best suitable to predict for the lycopene content. Now, further, the random forest models were developed. Random forest models were developed for the 500 number of trees, and those number of trees were taken into account for machine learning model development, which showed the lowest RMSE value. Similarly, support vector machine regression as well as neural network regression were developed. Now, because we had both linear as well as non-linear models, so linear models can be compared with the R-square value, while the non-linear models cannot be compared with the R-square value. So we have compared it with root mean square error on the test data set. And it was observed in the light of Occam's razor, it was observed that the multiple linear regression was best suitable. So multiple linear regression was best suitable in light of Occam's razor. Many of the times we enthusiastically go for the complex machine learning models. So I would like to stress upon this. Here it is explainable. Most of the machine learning models which are kind of black box, which we cannot explain. Here we can explain that these are the wavelengths which are varying. So the results are even much promising than the similar studies throughout the world. Next, apart from the regression models, I have developed the classification models. Classification has been done based on the lycopene content of tomatoes. Same machine learning pipeline has been done and development of both probabilistic and non-probabilistic models, including logistic regression, linear discriminant, random forest, ANN and SPM. So what we could identify is that 560 nanometer, this particular wavelength was very much varying with the lycopene content. So the results are very much promising as far as the classification is concerned. This has been done for fruit classification with respect to spectrophotometer for the first time. Because what are the spectrophotometers available in the lab? They just give us the spectra but don't have facility to have the classification over it. So by comparing the two, comparing all the probabilistic and the non-probabilistic models, it was identified that the artificial neural network was performing the best with 95% accuracy obtained from the confusion matrix on the test data set. Well, these are the papers published, and the IPR has been granted on 19th April this year. And similar studies I have done it for mangoes and for apples. The apple part is going on, and this one is the next in line. So I will, rather than the tabletop spectrophotometer, I will use the gun sort of in terms of edge device. And I extend my heartiest thanks to TinyML Foundation for giving me the opportunity, and my institute NIFTM as well as CSIR, CSIU for conducting this research. And I am open for collaborations for investors as well as startups, and I am open to discuss and share the license of the IPR so that we can have a good device in the market. But these sort of devices have huge potential, not only in the developed countries but also in the developing countries. Thank you so much. Thank you for having me.
Round of applause. Okay, we have time for some questions.
Hi, thank you. I think that my main question is, what is the use case for this technology? Because if I understood correctly, it's like for a health perspective, right? So I was wondering, what is the deviation in micronutrient content between something you define as a high quality and low quality food? Because if that range is not so huge, does it really have an impact on health?
Well, thank you. The research which has been done for tomatoes, it is the lycopene content was at the center stage. Lycopene content, it is linked with the reduced risk of cancer.
Yes.
So the lycopene content having the same wavelength which we have from the broad range of spectrophotometer, the 560 nanometer or the 535 nanometer, that is linked with the lycopene content if you look at the spectrophotometer available in the laboratories. So definitely the wavelength can change little bit depending upon the type of sensor which we use, like spectrophotometer or the SparkFun chipset. And also it depends upon the variety of fruit. So definitely we have to build up a library, a comprehensive library for it, so that we can have good, more advanced machine learning models, so that these spectrophotometers can be used for other fruits also.
Yes,
I hope.
I see. Okay, but can you tell us more or less the kind of micronutrient deviation that you can experience in these foods when you make your measurements?
Well, micronutrient explanation, micronutrients have, well, I have not captured micronutrients. Well, lycopene is the macronutrient which is
Yes.
available. Yes.
Okay.
Yeah. Yeah.
Thank you.
Thank you.
All right. Final round of applause for Dr. Arun Sharma. Thank you.
Thank you.